Question 19. Question is about the measurement of wavelength of laser light, very similar to the core practical that you've done. The light is shown on a diffraction grating at normal incidence. Light is transmitted by the diffraction grating, so passes through and produces spots on a screen, just like your core practical. These spots are labeled A to E in figure 1, and spot C is the zero order maximum. So that's n equals 0, n equals 1 on either side, and n equals 2 on the edges. And you have got distances that have been taken as measurements: A, B, distance between B and C, the distance between C and E. Okay, so a student uses a meter rule with 1 millimeter divisions to measure the distance between the 0 and the second order maximum. So there's a 0, there's a second order maximum. He uses readings to obtain measurements A, B, and C. These distances between the centers of the spots are shown here. So what we've got is a ruler used to measure A, B, and C, and here are the distances in millimeters, and these are the uncertainties in millimeters. Okay, so explain why the student's estimated uncertainty in the measurement A is greater than the smallest division on the meter rule. Now, as we've discussed in our lessons, when we take a measurement with a ruler, we have a half a millimeter uncertainty on one end and half a millimeter uncertainty on the other end. So if we were to use and measure the distance, so we will need to align our ruler at this position here, and we'll have to align our ruler in this position here. So aligning our scale on our ruler here will give us a half a millimeter uncertainty and half a millimeter uncertainty here. So the overall uncertainty on the ruler measurement should be plus or minus 1 millimeter, but it's actually 2 millimeters. So where has that extra millimeter come from? And it has come from, if we notice here, is the spot is actually quite wide. Okay, a little bit is not a tiny dot on a screen. So judging the center of that spot will produce additional uncertainty, and that's where that additional uncertainty has come from. So writing this out, the precision of the ruler is 1 millimeter, which they've told us in the question. Each side of the measurement has an uncertainty of plus or minus a half millimeter. That's due to the ruler, plus the uncertainty in aligning the ruler into the center of the spot. Therefore, there is a plus or minus 1 millimeter uncertainty on the ruler, as I discussed, and plus or minus 1 millimeter, that's where the additional uncertainty has come from, according to that number there. So where's that extra uncertainty come from? And it's due to aligning the ruler to the center of that spot on the screen. Hence the overall uncertainty is plus or minus 2 millimeters. Okay, part B, the distance between the center of spot A and C and the distance between the center of spot C and E are equal. Okay, so the distance between here and here and here and here are the same. Okay, and A plus B is equal to C. So these two distances are the same as that distance in total. And as we can see, that is true. That plus that gives us that there. 289 plus 255 gives us 544. Okay, it says calculate the percentage uncertainty on this in the sum of A and B. Okay, so the percentage uncertainty on the sum of A and B. So the percentage uncertainty in the sum A and B is the overall uncertainty on A and B over the value of A plus B. So what is the value of A plus B? Is 289 plus 255. And the overall uncertainty on A plus B is the sum of this plus this, because A plus B, there's an addition sign there. We do not find the percentage of A and the percentage of B and add those. This is an addition. We only go in with percentages when it's multiplication or division. This is addition, so we add the absolute uncertainty to get the overall uncertainty. So that will be the absolute uncertainty on A, which is 2, and the absolute uncertainty on B, which is 2. So the overall uncertainty on A plus B is 4, divided by the sum of A and B, which is 544, and times that by 100 to get it as a percent of 0.74%. Calculate the percentage uncertainty in C. That is, the percentage uncertainty in C is the overall absolute uncertainty in C, which is 2, divided by the value of C, which is 544, which is equal to, and times that by 100, gives us 0.37%. So the percentage uncertainty, so if we compare this right now, the percentage uncertainty in C is 0.37%, but the percentage uncertainty in A plus B is 0.74%. So getting this distance by taking two small measurements gives us more uncertainty than just taking one bigger measurement. Okay, so taking two smaller measurements gives us 0.74% percentage uncertainty. Taking one larger measurement, gives us 0.37%. Okay, so it's better to use the larger measurement, which is what the next question will be. Comment on which method is better for measuring the distance between zero order and second order maximum. So zero order is there and second order is there and there. So the best way to take the measurement is doing the direct measurement, because you have a lower percentage uncertainty on the direct measurement. So direct measurement from n equals 0 to n equals 2 is better because it has a lower percentage uncertainty. Part C of this question shows you the same figure again, but it shows you a plan view of what's happening. The laser light is shown on the diffraction grating, and there's your screen, and we see spots on the screen, and that's the distance from the grating to the screen, and the grating to point E, you got an angle of theta, and the distance to the screen is 1.28 meters. Okay, so 1.28 meters is the distance from the grating to the screen. And we know that the distance from there to there is 544 millimeters, as we've seen from the table, and that is 544 times 10 to the minus 3 meters to get that in meters. So what's the question? Calculate the angle theta. Okay, so we got to calculate this angle here, theta. That distance is 1.28. This distance is 544 millimeters. In meters, it's just divided by 1,000. And we use tan, as we've got the opposite and the adjacent. So tan theta is 544 times 10 to the minus 3 over 1.28, and that gives us 23 degrees. Next part of the question, it says spot E is the second order maximum, n equals 2. The diffraction grating has 3 times 10 to the 5 lines per meter. Calculate the wavelength. So we know that this is an interference experiment, and for constructive interference, what these spots represent, bright regions, n lambda is equal to d sine theta. So we have n, which is a second order maximum, n equals 2. So that is this point here, or that point there. We know the angle of the second order, as we've just calculated, 23 degrees. So we've got the angle, we've got n. We need to find d, the distance between two consecutive slits. And that's not given to us, but we can calculate that by finding out if we know there are 3 times 10 to the 5 lines that slits per meter, then we can find out what's the distance between two consecutive. So that's 1 meter divided by how many lines there are, and that is 1 divided by 3 times 10 to the 5. And that will give us the distance between two consecutive slits. So 1 meter divided by 3 times 10 to the 5 slits, and that is our D. So that's there. Sine of 23, that's the angle of the second order, and divided by n is the second order, 2, and we'll get a wavelength of 6.51 times 10 to the minus 7 meters. Now that in nanometers is 651 nanometers. This is in towards the red part of the spectrum, higher wavelength. So the visible spectrum between about 400 and 700 nanometers, and that number looks right. Part E, the final question. The student plans to repeat the experiment using the same diffraction grating and laser. State and explain one way the student can change the experiment arrangement to reduce the percentage uncertainty in the measurement of the wavelength. Assume that the percentage uncertainty in sine theta is the sum of the percentage of y and c. So what is y and what is c? So the percentage uncertainty in sine of the angle is the percentage uncertainty of that and the percentage uncertainty of that. Okay, so let's have a look at what's going on. We want to work out the wavelength. So this is the wavelength formula, the way we rearranged it, lambda equals d sine theta over n. So let's have a look at D. So we're going to make the assumption that the distance between the slits, that's relatively accurate. N we'll say is 2 as before. So then we are looking at Y and C. And we've just been told that the uncertainty on sine theta is the sum of the uncertainties in Y and C. So essentially, if these two, N and D, don't carry any uncertainties, the uncertainty in the wavelength is the uncertainty in sine theta. So the percentage uncertainty in the wavelength is equal to the percentage uncertainty in Y plus the percentage uncertainty in C, okay, as it says there in that statement there. So if we know the percentage uncertainty in sine theta, that is actually the same as the percentage uncertainty in lambda. So how could we improve that, and how could we improve that? Now, if we increase the distance, that we measure, this distance, if it gets larger, okay, the uncertainty in this measurement will stay the same, but the measurement will get larger. So the percentage uncertainty in y is equal to the distance, it's the uncertainty in y, which is plus or minus a millimeter if you use a ruler, divided by the distance or the value of y times by 100. So if this value gets larger, then this value will get smaller. So if we measure and move the diffraction grating further away, the percentage uncertainty in y will get smaller. The ruler that we use will still have a millimeter scale, so that uncertainty will remain the same. So increase the distance is one. The other is the percentage uncertainty in C. How do we improve that? That can be decreased. It can be decreased if the distance between the n equals 0 and higher orders are used. This reduces the overall uncertainty in lambda. So if we wanted to, let's say, use other spots which are further up, that would increase the distance there. So the percentage uncertainty in C will also decrease as well. So two things that we could do to improve: percentage uncertainty in Y can be decreased if larger distances from the screen are used. This reduces the overall percentage uncertainty in lambda, and also percentage uncertainty in C can be decreased if the distance between the n equals 0 and higher orders are used. This reduces the overall percentage uncertainty in lambda as well. So if this drops, or this drops, and that drops also.